Have you ever stopped to think about how a video you click on finds its way from a server halfway across the world through this massive web of connections directly to your screen? Well, it all boils down to a digital address. Today, we are diving deep into the Internet's address book, the story of IPv4 and its much bigger successor, IPv6. So here's how we're going to break it all down. First, we'll get into what an IP address even is. Then, we're going to take a trip back in time to look at the original system, IPv4, and find out why it basically caused a digital real estate crisis. After that, we'll meet the hero of the story, IPv6, put the two systems side by side, and then we'll wrap up with why this massive change to the Internet's plumbing matters to every single one of us. All right, let's get into it.
First things first, let's demystify the IP address. Honestly, the best way to think about it is like the postal service for the entire digital world. It's the whole system that makes sure every little piece of data gets exactly where it needs to go, no exceptions.
So think about it. How does the internet find you? It's just like sending a letter, right? You need a house number, a street name, a city, a postal code. If you miss any of that, your letter is just lost. The internet is pretty much the same, but instead of houses, we've got billions of devices.
And that's exactly where the IP address comes in. It's really just a unique number that gets assigned to every single device that's connected to a network. Your phone, your laptop, that smart TV, the server hosting your favorite website, they all have one. It's what makes sure all those little data packets, the tiny pieces of your emails and videos, arrive at the correct digital doorstep.
Okay, so let's jump back to the early days of the internet. The very first addressing system they came up with was called IPv4. You can think of it as the original blueprint for the entire internet neighborhood.
I guarantee you've seen an IPv4 address before. It looks something like 192.168.1.1. Technically, it's a 32-bit number, but to make it easy for us humans to read, it's broken up into 4 numbers separated by dots. Each of those little sections is called a quad, and each one can be any number from 0 all the way up to 255.
So in the beginning, to keep things organized, the engineers created something called address classes. You know, think of it like how a city gets zoned. You've got these huge industrial districts for giant companies, some medium-sized commercial blocks for businesses, and then all the small residential streets for individual homes.
And this table right here shows you exactly how that worked. A Class A network was for the giants. Think huge corporations or universities, giving them space for over 16 million devices. Class B was for medium-sized outfits. And Class C, which was the most common, was for small networks with up to 254 devices. It was a bit rigid, sure, but it was a simple way to hand out addresses.
Okay, so you have this address. How did a router know which part was the street name and which part was the specific house number? Well, that was the job of the subnet mask. It's another 32-bit number that basically draws a line in the sand. It tells the router, hey, this part of the address is the neighborhood, and this other part is the specific house in that neighborhood. Now, this whole system actually worked pretty well for a while. But then the internet just exploded in popularity, and a huge problem started to bubble up. We were facing a full-blown digital real estate crisis. The original neighborhood just wasn't big enough for everyone who wanted to move in.
And here is the root of the problem. Because IPv4 addresses are 32-bit, you can only have a maximum of about 4.3 billion unique addresses. Back in the 80s, that number seemed astronomical, almost infinite. But by the 2000s with PCs, then laptops, then smartphones, well, it became very clear we were about to run into a wall.
I mean, it all boiled down to one simple, scary fact. The internet was running out of room. The number of devices needing an address was skyrocketing, and we were getting dangerously close to using them all up. The neighborhood was full, and it was time to build a whole new universe.
And that, of course, brings us to the solution. Internet Protocol version 6, or IPv6. Now, this wasn't just a patch or a small upgrade. It was a complete reinvention of internet addressing, designed from the ground up to be, for all practical purposes, completely inexhaustible.
Just look at that number. It's 340 undecajillion. That number is so ridiculously huge, it's hard to even comprehend. To put it in perspective, that's enough IP addresses to assign one to literally every single atom on the surface of the Earth, and still have enough left over to do it again over 100 times. So yeah, the address shortage problem, it's solved. For good.
So what does one of these brand new addresses actually look like? Well, I'm not going to lie, it's a bit of a monster. It's 128 bits long, and it's written in hexadecimal. That means it uses numbers 0 through 9 plus the letters A through F. At first glance, it looks super complicated, but don't worry, there are a couple of really clever rules to make it much simpler.
So how do we tame that beast of an address? It comes down to two simple tricks. First, you can just chop off any leading zeros in any of the blocks. Second, you can find the longest string of blocks that are all zeros and replace that whole section with a double colon, a dash dash. You can only do that once per address, but these two rules make these gigantic addresses so much easier to write down and work with.
All right, now that we've met both of our contenders, let's put them head to head. It's time to look at the key differences and some of the really cool upgrades that came along with this new system.
So the most obvious difference, the one we've been talking about, is just pure size and the way we write them. IPv4 is 32-bit and uses those familiar decimal numbers. IPv6 is a whopping 128-bit space and uses hexadecimal. This is the fundamental change that completely solves the address shortage problem.
Now remember that old clunky Class A-B system? It was pretty wasteful, so along came a much smarter method called classless inter-domain routing, or CIDR. It just uses a slash and a number to tell you exactly how many bits of the address are for the network part. This gives us incredible flexibility and lets us hand out address blocks way more efficiently than the old system ever could.
You know, another brilliant little trick they came up with to make IPv4 last longer was the idea of private addresses. The best analogy is internal phone extensions in a big office. You can dial a 4-digit number to call your coworker, but that number is totally meaningless to anyone outside the building. Private IPs work exactly the same way for all the devices on your home or office network. And here they are. These are the most common private address ranges. I'm willing to bet that 192.168 address looks really familiar, right? It's probably what your home router uses. These special blocks are reserved just for local networks, and they can be reused in millions of homes all over the world without ever causing a problem on the public internet.
Okay, so we've covered a ton of technical stuff, but why does any of this really matter? Why should you care about this switch from IPv4 to IPv6? Well, because it's not just a technical upgrade. It's what powers the entire future of the internet. At the end of the day, IPv6 is what lets us keep innovating. It unlocks basically limitless growth for the Internet of Things, connecting everything from your smartwatch to your refrigerator to the sensors running our cities. It also makes the internet more efficient and even more secure, with security features baked right into the protocol itself.
And that really just leaves us with one final big question. We've officially moved from a world of digital scarcity to one of near infinite abundance. The question is no longer if we can connect something to the internet, but what will we connect next? So what do you think? What will the next billion devices on our ever-expanding internet actually be?